So now we've entered the part of the course that has to do with scaling, and we're going to do a series of case studies where, by simple dimensional arguments, we're going to actually generate very deep insights. And probably one of the deepest of all has to do with the scaling of diffusion time. So before I even address the topic in general, we need to unpack those words. So first of all, diffusion. Diffusion refers to the random hopping around of molecules, for example, in solution. They're jiggling around, and the way I think of it is that at every instant, the molecule flips a coin to decide to go right or left, forward or backward, up or down, and such a sequence of coin flips leads to a trajectory which is known as a random walk. And that random motion is what we know as diffusion. Interestingly, when you have many particles, many molecules conspiring together, and each of them is acting independently, each of them is flipping coins, nevertheless, that gives rise to an effective behavior which is deterministic and very well characterized. And I think that that's a really beautiful thing related to some of my earlier discussions about the role of phenomenological laws and insights. So the kinds of questions that we're going to address is we're going to ask the question, how long does diffusion take? And to make that concrete, I want to pose the following challenge, and it's a thought question for you. So the question is, when Usain Bolt or some sprinter hears the starting gun at the beginning of a race, the moment that the brain registers the starting gun, then there's the propagation of a signal down the nerves to the feet so that the runner can start running. And the question I ask is, which process is faster? The propagation of the action potential along the axon, or alternatively, the diffusion of neurotransmitters across the synapse, like you see here. So, this region right here is the synapse. It's around 30 nanometers across, let's say, and neurotransmitters, they basically diffuse across that gap in order to bind to the ion channels that you see over here, and the binding to those ion channels then leads to the opening of those channels and subsequent propagation. So that's question number one. We want to know, what is the diffusion time? We want to calculate how long does so our question is, how long does a molecule take to diffuse a distance? L. So that's a question we want to ask. And a second example, which I quite love, is related to an experiment from the 1960s, which I show you here. So the idea was that a radioactive tracer particle, I think it was radioactive leucine, but I'm not entirely sure, as you see at the top here, is released over here. And then over time, using radioactivity, one watches the propagation of the radioactive leucine as it diffuses or perhaps is actively transported down the nerve. And so, the picture that you might have is shown in this cartoon where we have this radioactive amino acid, and now each one of these amino acids has the capacity to do coin flips at every instant, and over time the radioactive leucine will spread across the cell, and we're curious about whether 16 days to travel 30 millimeters is a long or a short time. We want to have an intuition a priori as to whether or not that's a short or a long time. So those are kind of my two puzzles that set the stage for the bigger question, which is, how long does a molecule take to diffuse a distance L? So what I'm after is some expression, some formula, basically, that tells me how to relate diffusion time and the distance over which a molecule is diffusing. In order to make progress on this, we need to actually think a little bit more about the diffusive process. And to do that, I need to introduce a few ideas. So, I want to introduce the notion of, so I have some boxes that are adjacent to each other, as I show you here. And what I want to find out is I want to find out how much material. So let's imagine that there's a bunch of molecules in this box, and then there's some number of molecules in the next box, and there's some other number of molecules in the next box. And what I'm trying to find out is I want to know how much material flows across this interface. So flux across the plane. And the flux is defined as number of molecules crossing unit area per unit time. So that's the definition of the flux, which I'm going to label by by J. J is the symbol that I'll be using for fluxes of various kinds: flux of heat, flux of particles, flux of momentum. In all cases, I'll be using the letter J to represent that. So the question is, this is a question for Wilson. We're on the desert island. I airdrop you in a question. And the question is, how does the flux depend upon the concentration in adjacent boxes? So that's what I want us to figure out. How does the flux vary as a function of the concentration? And probably the nicest way for us to think about this is by appealing to this picture. So as I say, on the left you can see here that there's a plane and there's some molecules on that plane, and they have a concentration C of X. And then on this other plane at position X plus delta X, there's a different concentration. And the thing I want to find out is, how does the flux depend upon this concentration? And what I'm hoping that you're going to say to yourself is, well, okay, so I somehow want a relationship between the concentration and the flux. And let's try to unpack this. So the first thing that I'm observing is that the flux should somehow be proportional to the gradient in the concentration. So it's interesting to think about what that actually means. The quantity that I calculated is the change in C over the change in X. So if I take a little step in the X direction, how much concentration change will there be? If the concentration is uniform, then we expect that the flux should be 0. So somehow it's got to depend on the difference in concentration from one plane to the next. And we have the intuition that the larger that concentration difference, the larger the flux will be. A simple way to see that, by appealing back to this picture, is that if I have way more molecules on this side, and all of them are flipping a coin, then all of them are either going to step in this direction or that direction. And in general, it's going to be n over 2. Half of the particles are going to jump this way and half are going to jump that way. And the same is true for these guys. So if there's more particles on the right than on the left, there will be a net flux from right to left, because just by chance, more particles flipped a coin saying jump that away, because there's more particles over on this plane. Okay, so basically the point that I'm making is that the flux is going to be proportional to delta C over delta X. Why did I put this minus sign? I put the minus sign because if dC by dx is increasing, if the concentration gets larger as I move in the positive X direction, then that means that the flux is going to be in the negative X direction. Why? Because, as I just said, stuff flows from high concentration to low concentration. So if dC by dx is positive, if the slope is positive, stuff will move to the left, so I need this minus sign. Now, the units of this thing are not correct. So there's a constant of proportionality And that constant of proportionality is called the diffusion coefficient. So this whole law that we're articulating here, it's a phenomenological law, is called Ficks Law. And one of my big themes this term is going to be my what do I want to say? My deep support for phenomenology and for phenomenological laws. I like them. I appeal to them without apology. And in fact, I reject the idea that the only kind of mechanism is one in which you state what the nature of the molecular players is. That's just not true. There's all sorts of mechanistic insights that come at different scales. And sometimes they're not molecular, sometimes they're more at these larger scales, and they're phenomenological. So how do we think about the units here? Well, on the left-hand side, we have number over length squared time. Why? Because I said flux is number per area per time. Over on the right-hand side, delta C by delta X, that thing has units of number per length cubed per length. The number per length cubed is the concentration part. So let me highlight that. So that's the concentration. And then the 1 over delta X has got units of L. And so now we're prepared to try to make a guess about what the units of D have to be. And the reason we're prepared to do that is we've got to balance units on the two sides. So on the left, I have number over L squared T. And on the right, I have number over L fourth. That means the units of D have got to be L squared over T. All right, so just by dimensional arguments, I know that the diffusion coefficient has got units of length squared over time, so microns squared per second, or some examples like that. So typical diffusion coefficients that you might want to carry around in your head. So for a protein, I'm going to just say something like 10 microns squared per second. And for an ion, I'm going to say something like 10 to the 3 microns squared per second. Okay, so what have we done? What we've done is we've basically asked the question, what is the nature of flux? And the nature of flux is that it tells us about how much material is transported across planes. And we can have flux of volume, we can have flux of molecules, we can have flux of momentum, we can have flux of temperature or heat. There's all sorts of different options for what is fluxing, but the concept is always kind of like I just wrote. So I wanted to foreshadow also that the Ficks Law is really an interesting first example for us of a much more general concept. And here it is. Many, many examples of flux in systems that are not in equilibrium will be linearly related to the degree of disequilibrium. For example, when we think about flux of heat, J sub Q, then that will be linearly related to the gradient in the temperature. When we think about flux of momentum, we'll invoke the Newtonian law of viscosity. Again, and Ohm's law for the current flux and how it relates to electric field. All of these are examples of flux being linearly related to degree of disequilibrium. So I'm excited about that as well. So now we've got our diffusion coefficient, and what we're ready to do now is to try to estimate the time that it takes to diffuse, and to do that we're going to invoke dimensional analysis. Okay, so here's the way that I would like to think this through. So the question we're going to ask is, how long does it take to diffuse a distance L? That's it. That's what we want to know. And the way that this goes is it might almost seem like pulling results out of thin air, but the thing you do is you try to think about what would the quantity of interest depend upon. In other words, well, it clearly is going to depend on how far the particle is going, so that's L. It's got to depend on that. And different molecules, as I just showed you, an ion has a diffusion coefficient of 1,000 microns squared per second, and a protein has a diffusion coefficient of 10 microns squared per second. And so it shouldn't be surprising that an ion will cover the same distance in a shorter time than will the protein. It diffuses more quickly, okay? So what I'm going to do is I say, well, I'm going to write down this scaling relationship. I think that the diffusion time, as shown here, the diffusion time, that's a time, as I show below. So the units here are time. And then that should be a function of, and I'm going to write it this way. Very often I'm going to say, well, it's the distance to some power that I don't know yet, and then the diffusion coefficient to some power that I also don't know yet. And so the way that I proceed at this point is I say, well, look, I know that the left-hand side has units of time. And so that tells me straight up, since on the right-hand side, the only quantity that involves time is the diffusion coefficient itself. It tells me, aha, beta has got to be -1 so that I end up with that time in the numerator. So now I've determined that the diffusion time scales like 1 over the diffusion coefficient. Now we just have to figure out, well, how does it scale with L? And the way to think about that is I don't want to have any lengths left. It's a time on the left-hand side, so I need to get rid of the lengths. And so that means that L has to come into the second power such that the L in the numerator squared will cancel off the L squared in the denominator due to the diffusion coefficient. So that's it. I mean, that's our first example of using dimensional analysis in order to obtain a scaling estimate for some quantity of interest, which in this case is the diffusion time.